Perfect. Hi, guys. See more of you guys are joining now. Welcome to the second Concordium Educate and the second webinar of this. Today we are joined by a new speaker. We have Daniel and Dragos again, ready to look into a deeper dive into the identity of Concordium and their on-chain identity layer. Particularly, we're going to be looking at how exploring how identity works, how privacy is preserved, and then the role of zero knowledge proofs as well. We'll format this session by the first half. Dragos is going to lead it. And if you guys have any questions, just chuck them in the chat throughout, and Dragos can answer them. And then if we have time at the end, we'll do a bit of Q&A as well. And then in the second half of the session, Daniel's going to take over, again, dropping questions in the chat. Should we get the chat going now as well? Just if you let us know where you're joining us from, and then we can get started, and I'll let Dragos take over. Okay, let's change. I'll change the view to speaker. Okay, all yours, Dragos.
Hello, everyone. Thank you for attending the second webinar in the Concordium Encode series. Now we'll be talking all about identity. So we'll do a deep dive into how Concordium's identity layer works and the science behind it. For a bit of an overview of what we'll cover today, the first bit that I'll be doing will be an overview. We'll mention the problem with identity on public blockchains, Concordium's approach, privacy and accountability, the key participants and the separation of powers, principles of privacy. We'll explain how to get a Concordium ID and how to actually create an account using our wallets. And then we'll actually mention the identity disclosure process with 2 examples of legal scenarios. And finally, we'll be shortly mentioning Web3 ID, which is extending the base identity model. And then part 2 will be about the science behind the identity layer. We'll talk about self-sovereign identity, verifiable presentations as the solution. How do we prevent cheating? With those will be where zero-knowledge proofs come into play. And at the end, Sigma protocols and bulletproofs. Now let's proceed. So the problem with identity on public blockchains, how it's done today, you have extreme balances in the market. So you have either fully anonymous blockchains where you have Monero or Zcash, for example. There, even though it's private, you have no accountability, bad actors can operate with impunity, so this leads to a regulatory dead end. On the other hand, you have pseudonymous but trackable. So here we could mention Bitcoin or Ethereum, for example. In this scenario, transactions and accounts can be traced, but there is no actual systematic way to discover the real world identity behind them. This would lead to a worst of both worlds for many use cases. So you're not actually fully private, but at the same time, if a bad actor wants to do something malicious on the chain, they might be able to hide behind a bunch of accounts. Now, this means that neither approach works for serious business adoption or regulatory compliance. Concordium's approach. That's a QR code that you can scan leading to a page on Concordium ID. It delves a bit deeper into it. And there's also a link to a research paper. Now, we provide privacy by default and accountability when legally required. So every account on Concordium is linked to a verified real-world identity, but personal information never exists on chain, encrypted or otherwise. No single party can connect your identity to your accounts, and we'll explain this better in the next slide. Only a multi-jurisdictional legal process involving court orders can break this link. And this is all guaranteed by cryptography. It's not a policy that we enforced. It's actual math built into the protocol itself. The identity layer is also proven secure in peer-reviewed research. And there's a link to that research if you scan the QR code. Now, the core of the identity layer is Concordium ID. So this is a protocol level identity system. It's not optional. It's not a third-party add-on. It's actually built into the protocol itself. This means that you cannot hold an account without a verified identity. It enables for account creation, transactions, and then zero-knowledge proofs of identity attributes. It also supports both individuals and businesses. Now, the key participants in the system are going to be the users, first of all. So this would be individuals or businesses, the actual identity holders, the account holders, actually. Then we'll have the identity providers. They perform off-chain identity verification and then issue identity credentials based on that. We'll mention them in a couple of slides. We then have the privacy guardians. So the privacy guardians hold the cryptographic keys that are actually required for the disclosure process. These are typically legal firms. Currently, they are based in Switzerland. Each privacy guardian is approved by the Concordium Foundation, and there's a threshold of 2 out of 3 privacy guardians in order for their vote to actually count. Finally, we have the authority. So this can be any entity. So for example, law enforcement that has obtained a court order and then will initiate the disclosure process. This is actually the only party that can ultimately reconstruct the full link between identity and accounts. How this works, and an important bit behind this, is the separation of powers. So no single party can link an identity to an account. As you can see in here, we have the identity provider. They know your real-world identity and they have your documents and records, but they don't actually know which one is your wallet address. So when you create an account based on an identity, the identity provider has no idea that it's you that made that account. Then we have the privacy guardian. They hold just a key share that's needed for decryption, but they don't have access to any personal data. Concordium provides the protocol and chain itself and the infrastructure, but has zero user personal identifiable information. And then the authority, they have court orders and will coordinate this entire process, which in order for everything to happen, there has to be an actual legal process behind it. So for example, no agency can just come and say, what's that account behind, who's behind an account without an actual court jurisdiction. So there is no direct communication between the identity providers and the privacy guardians. The authority always sits in the middle. To delve deeper into this, we have the identity provider. They have access to your real-world identity and the documents. What's hidden from them is going to be the wallet address, the accounts, all on-chain activity. They never learn which account you create. The privacy guardian only has an individual share of a decryption key, which alone is useless. So they don't see any personal data. They never see names, documents, or identity records. Concordium only has the protocol, the chain, and the infrastructure, but doesn't hold, see, or have access to any information about the person. And then the authority will only know what the full legal process unlocks. Now, getting a Concordium ID, you can again scan this QR code, which will lead you to a page on our technical documentation for how to set up a wallet and get an ID. But to explain the process a little bit, first of all, you need to download the Concordium wallet. We have options for mobile, desktop, and web. Then you can start identity creation by selecting an identity provider. You will have to scan a valid identity document, assuming you do this on mainnet. On testnet, it's a much easier process. You just get a mock identity since it's testnet. But on mainnet, you need to scan your actual passport or ID card and then complete a liveness check. This would be a selfie or a video to actually prove it's you behind that ID. As an alternative, if you're from Denmark or Finland, you can use your EID directly for verification. You can skip most of the steps. Now for businesses, the process is similar, but there is obviously additional documentation needed. So the registration number, the registered address, director details, etc. Then once the IDP receives all that, they will verify the document validity. If everything is valid, the credential will then be stored in your wallet and the IDP's database. So nothing on chain. After you create an account, after you get the identity, you will be able to create an account. After you create the account, the IDP does not store where your wallet address is because the account creation happens separately. Now let's see how that happens. So first of all, to mention the current identity providers that are available on mainnet, we have Digital Trust Solutions. This is a general purpose high assurance identity verification for broad use cases. Then we have Nota Bene, which specializes in crypto-specific regulatory requirements. So in this case, it would be particularly the travel rule. And then we have Global FinReg, which focuses on financial regulatory compliance and institutional standards. If none of the current identity providers meet your specific regulatory requirements, contact us directly to discuss onboarding additional providers. Now, from identity to accounts. So before you got to the end of that process, and now in your wallet, you will actually see one identity credential. Once you have it, you can then create one or more accounts on chain. Every account creation is actually a transaction that goes on chain with zero knowledge secured with zero knowledge proofs. The chain will verify your credential validity without actually accessing any of the personal information that's stored behind that identity. This leads to flexibility by design. So multiple accounts can be created from a single identity credential. You can actually have up to 26 accounts per identity, but then a single wallet can hold multiple identity credentials, so you can have even more than that in your wallet. Privacy by default, so you may selectively reveal specific attributes on chain. Now, a best practice that we would suggest is to avoid revealing attributes unless completely necessary. So for example, if you go on a website and they just ask you to verify your age, let's say, you're not actually revealing an attribute because you're doing a range proof. And instead of saying I'm 26, for example, you will say I'm between 18 and 99. You won't actually reveal your specific age. All right. An encrypted public holder identifier will link your credential to your account. Decrypting it requires court orders and multiple privacy guardians, and we'll go into that process at the end of the presentation. Now, this is a diagram that explains going from an identity to accounts. So you have the user that first gets the wallet, then you go into IDP verification, a credential will be issued, and at the end, account creation will happen through an on-chain transaction with zero knowledge proofs. I see a question in the chat where the identity credential is stored. So that's actually only stored locally on your device and in the identity provider's database. But the identity provider, even if they have your actual identity credential, they don't know that that it's you behind an account. So it lives in your wallet or in the database. All right, this is another diagram showing how you go from a wallet where you have a seed phrase as any normal crypto wallet. You have an identity credential, one, let's say, that you got from Nota Bene. Then you can have 3 accounts on that. You can do activities with those on chain, and then you can have a separate identity credential in the same wallet that you got from a different identity provider. Now, let's discuss the 4 types of proofs just for an overview that are available with Concordium. So the whole idea of this is to prove not to reveal any information. So you're showing less of your data while proving everything that you need to prove. All of the proofs are generated locally in the wallet, so the verifier never sees the raw data that goes into it. All that a verifier would see would be the proof itself, and then it would just say yes or no. So for a bit more context, a verifier is a piece of software that you can see on our GitHub, which you just send a zero knowledge proofs to, and it will give back yes or no if it's valid or not. So for the first proof that we have, this is the one that we recommend to use sparingly, reveal attribute proofs. This will share the actual value. So for example, how it would look, you will be saying my country of residence is Denmark, let's say, or my name is Dragos. Then we have range proofs. This you use for a value to prove that it falls between a range. So you can say that I am between 18 and 65, and the birth date will stay hidden, while, for example, a merchant that is selling wine in the UK, let's say, will be able to then say that you are not a minor, but will not know your actual age. We have set membership proofs, so the value is in a given set. A use, for example, of this would be to say that I am an EU citizen, but I don't have to mention the country that I'm from. And we have the opposite of that, which are going to be set non-membership proofs. This will be when the value is not in a set. So you can say in this case that you're not from a sanctioned country, for example, when you want to do certain activities. The underlying cryptography behind this, which will be mentioned in the second part of this webinar, and my colleague from the science department will explain it better than I can, will be the Sigma protocols, the Fiat-Shamir transform, and bulletproofs. The Sigma protocols and Fiat-Shamir transform are used for equality and inequality proofs, and set membership and non-membership, and then bulletproofs are used for range proofs. Now, the process that I mentioned before for identity disclosure exemplified. So this will happen only with valid court orders, and no single party can act alone. We have the authority that sits in the middle. They will hold court orders, coordinate this entire process. On the left side, we have the privacy guardians. They hold decryption key shares. And on the right side, we have the identity providers, which hold the identity records, but have no access to on-chain data. We have two scenarios on here. So first of all, if the question is who owns this on-chain address, the authority will get an encrypted identifier from the chain. That's useless by itself as it's obviously encrypted, but then the privacy guardians will get together and they need 2/3 in order to actually decrypt it. The authority will reconstruct it. Then the identity provider will need to match that identifier to actually say that that identifier leads to this identity, and will then return the actual identity behind the account. And then in the second scenario, we have the opposite of this. So we can say what accounts does this person have, and then the authority will send all of the person's data to all of the IDPs. The identity providers will return records with encrypted linking keys. The privacy guardians will then decrypt, and at the end, the authority will retrieve all of the accounts behind an identity. This means that in cases of a bad actor trying to do something illegal on chain, it would be possible to actually find out who that person is. Finally, for a short mention, it's Web3 ID. So this extends the entire model. Concordium ID, everything I've mentioned before, is the foundational layer. This is required for every account on chain. And Web3 ID builds on top of it for a much wider range of verifiable claims using the W3C verifiable credential standard. In this case, anyone with a Concordium account can become an issuer. Issuers manage credential lifecycle, so expiration or revocation via smart contract. Zero-knowledge proofs work identically. You can mix both Concordium ID and Web3 ID in a single proof request. And we also offer developer tooling, so this would be template smart contracts and an issuer tool. In practice, what Web3 ID is used for, a university, for example, could issue diploma credentials that employers could instantly verify with a zero-knowledge proof. But this applies to any scenario, as in this case, you are going to be the one that will be issuing the credential. So let's say that you represent the university. You will issue a diploma credential. Then if I attended that university, I will be able to get a credential from it. And if anyone asks for my diploma, instead of actually showing that, I could do a zero-knowledge proof proving that I've attended the university. Now, the key difference from this and Concordium ID is that Web3 ID credentials are not part of the identity disclosure process, and there are no restrictions on who can issue them. So in this case, trust depends on the issuer, not the protocol. Now, for a short recap before I hand off, every account on chain is linked to a verified identity in a private manner. There are 4 participants in this system with strictly separated powers. Personally identifiable information is never stored on chain, so no single party can link identity to accounts. And there are 4 zero-knowledge proof types: reveal, range, set membership, and set non-membership. Disclosure is only possible through a multi-jurisdictional court process. And finally, we have Web3 ID, which extends the model for any verifiable credential. right. I'm seeing a message in the chat. Remind us of the 4 parties. So you had the privacy guardians, you had the identity providers, the Concordium chain itself, and then you had the actual users. Those are the 4 parties that I was referring to. And another question in these cases that I mentioned, the user should be identified for the issuance of an academic credential. Yes, but not necessarily, as this is entirely up to the one that issues the credential. But yes, when you, let's say you attended the university, you should be identified by the university in order to actually receive that credential. But the process in which you do that, it's all up to you, since this is done through smart contracts. It's not done in the manners I explained before. So that's how Web3 ID is a bit different. Now, for the second part of the presentation, I want to hand off to my colleague Daniel. He's part of the science department, so the actual brains behind all this, and he will start by discussing self-sovereign identity.
Okay, thanks. Can you give me the screen so that I can share my part? Excellent.
All right, you should have it now.
Yes, got it. There you go. I mean, no surprise, we continue at the same slide. Maybe just for the funs of it, there's one Q&A question, I think, which I can probably talk about now already. So this is about this, like, question is, okay, well, what if I have an ID, and in my country, privacy is required, but the service provider, the merchant, they need to know certain information about me. Again, first, I'm not a lawyer. I'm a scientist. I'm a cryptographer, so don't take any legal advice from me. But what I would assume here is, from my point of view, is this is a self-sovereign identity system. So that's between the user, the holder of the credential, and the merchant. So it's a legal question for the merchant whether they can ask and accept such a proof or not. And the same for the user, whether they're allowed to give that proof. The chain itself has nothing to say in that regard, as we'll see. Yeah. Can you still see my screen?
Yeah.
Good. All right. So this is the background of this identity system. So background on me, I'm one of the cryptographers that was designing this. And so I can give you a bit of an overview of what this is about and why we care about this. So self-sovereign identity. We'll start with the following example, right? I mean, let's say the user wants to buy some alcoholic drink. Very simple, right? You go to the store, you get a beer, you pay, done. Now, if someone too young tries to do that, and that's of course a problem, authority is not so happy about that. So in most countries, there are certain limitations about to whom you can sell alcohol. And so that means in a real store, what typically happens is that, of course, you go with an ID. So what happens is in your typical store is you go there, you show them your ID, they check it and make sure it's not a forgery and whatnot. And if you're an adult, you can get the drink. Now, from a privacy point of view, there's some concerns here. So clearly, if I show my full ID card, physical ID card, the shopkeeper can potentially learn everything about me, like my name. They don't need to learn my name for me buying alcohol. All that is relevant is, in fact, my age. So even my exact birth date is not really information they should have. Still, traditionally, they would get that. Now you could say, well, okay, fancy us. If you're lucky and you're in a country that has already some form of EID system, I don't know, say one of the Nordic countries, you could use an EID in an online store. But the problem there is that in these traditional EID systems, usage might leak that to the government. So each time you want to use the ID, basically you tell a government server like us, signs a message. And then that means the government kind of knows where you're using your ID. Now, for some things, you might not care, right? If you say go vote, fine. But you might visit some web pages you don't want the government to know that you visit them, right? And so ideally, we can avoid that. And this brings us to self-sovereign identity. Here, the idea is we have three actors. We have an issuer, a holder, and a verifier. And the design goal of self-sovereign identity, and this is nothing we have come up with, this is a known concept, means that the user here is empowered. They have full control over their identity. Now, in terms of what these actors can do, so we have, of course, the issuer. They are the ones issuing you some form of credential. In our case, for the accounts, the identity provider give you an identity credential. But as Drago said before, it could also be your university issuing you a university diploma. Intuition here, of course, is when they issue a thing to you, they do some checks to ensure that you are deserving that credential. Then, as a user, you hold that credential, typically in a wallet. And then we have a verifier, say a merchant, that then can get information about you by looking at said credential. So a bit more about the identity issuance here. We have this at the case of the identity provider. So in Concordium system, you go to their webpage via your wallet, and you need to actually show your ID credential, depending on what you have. So in the normal case, what that means is you have to take photos of it, you have to upload it, and you probably, in today's world, have to do some weird video dance where you do some movement to show that you're not an AI-generated deepfake image. And then they create kind of a digital copy of that passport, driver license. And this identity credential is valid for 5 years. And the process itself is not really new. I mean, you know this probably when you sign up for an online bank. The difference, though, is when you sign up for an online bank, right, the information for this identity check directly goes to the bank. They learn probably a lot about you. Here, the credential doesn't go to the blockchain at all. It goes to you, the user, into your wallet. So it's only between you and the identity provider at that point. And so then we have this picture. We have now the user with this certificate here in the middle. And they can go and, of course, talk to a businessman, the verifier, yeah, and make a statement about this credential they have. And for the businessman, this is acceptable, but only under the assumption that they trust the identity provider. This was probably a question before, right? When it was like, yeah, but anyone could issue a university diploma in the Web3 ID system. And the answer is yes. In this add-on credential system we built, anyone can be the issuer. And there it is really important that you as a verifier select the ones you trust. Hence, this is, of course, in some cases a difficult question. And so for the core system, the blockchain itself has, the foundation has selected a fixed set of identity providers which are more trustful. We have selected them carefully. And so there the idea is kind of that you as a verifier have an easier task in trusting them because they have been pre-selected. But in general, in a self-sovereign identity system, anyone could be an issuer and a verifier there. Okay. So here's how identity verification works, a bit simplified. You know, you go, you send your certificate to the verifier. And so what you need to do here, right, is that you basically check the digital signature on that credential. So here maybe a bit of cryptographic background. If you get a verifiable credential issued to you, it's basically a text, you know, the attributes, and then digitally signed by the issuer. And so if the verifier knows this verification key, which they should if they trust the issuer, they can verify that, of course. The good part here already is that the issuer does not learn about the usage of this. This is between me and the verifier. In particular, the issuer does not learn how much I use my credential, where I use it, at which time. I have full control over that. And the verifier only needs to know some basic meta information about the issuer, which they, for instance, in our case, can get from the blockchain. So they don't even need to talk to the issuer to have, say, this public key. They need to verify a credential. But this simplified version is still a bit bad because it kind of resembles the old school version of like me giving my ID card to the shop owner, right? They see all the attributes there. And in theory, they now have a copy of my credential. And so they could take that credential to someone else, show it to them, and they would also be convinced about these statements because, again, they can check the signature key. So we should do better. And that's kind of the idea. We do a so-called verifiable presentation. Again, this is a concept which is kind of commonly known in this space. So instead of showing your credential directly, you build a so-called derived credential. And this only contains specific claims about you, the claims you want to make. For instance, the classic one is for the beer here is I'm older than 18. So give me the beer, please. So this is, of course, easy to do. At first, you just take your credential. You see if you can set the derived credential. And if yes, okay, send that to the businessman. Problem, though, is how the hell do you now verify this? Because at first, now the problem was, check a signature, right? That's easy. But now I build a new object which has not been signed by the issuer. And so this becomes a bit more problematic. Now, there are some ideas how you can do some simplification of that. For instance, every attribute could be signed by the issuer, so you could at least do partial reveals, but it becomes a bit clunky. And so in comes a new technology or a new technique, zero-knowledge proofs. Now, it is not that new, to be honest. We know about zero-knowledge proofs in cryptography for decades now. But in some sense, this is the magic of cryptography. So what is this about? Okay, so we have here Alice and the rabbit. And Alice now says, oh, here's a very hard Sudoku. Rabbit probably tried it, but failed. And so she claims she knows the solution to that. And so Rabbit, of course, is a bit skeptic. And so it's like, okay, prove it to me. Now, the easy way Alice could do is she could send the solution to the Sudoku. Rabbit can prove it very efficiently. I mean, if you ever did that, it's easier to check a solution of a Sudoku than actually solving it if it's a hard Sudoku. So that would be simple. But on the other hand, that would also mean that Alice has now revealed information to Rabbit, right? Rabbit can now take the solution and go to someone else and say, you know, I have solved the Sudoku. So if Alice wants to keep her secret, she has to do better. And the idea is she uses a so-called zero-knowledge proof. Here, the intuition, again, is that Alice and the rabbit go into a protocol, a discussion, where after this discussion, Rabbit should be convinced that Alice indeed knows this Sudoku solution. So you can think, I will not go into the details how this works. I mean, that could be its own lecture. But the idea you need to imagine is that Rabbit basically challenges Alice on this. And then later on, Alice needs to respond in a certain way, which then should convince Rabbit here. This can be extended, of course, to more mundane concepts, such as public keys and secret keys in a crypto system. So, for instance, you have an account on a blockchain. You can prove that you are the owner of the account by proving that you know the secret key without revealing any more information about this. I should also mention here that traditionally, if you look at zero-knowledge proofs, how they are written down, if you go to Wikipedia after this talk to read up on it, they're often displayed in an interactive way. So as I said, as a discussion between Alice and the rabbit. Though in practice, this is not great because it means that you now need to be online at the same time and whatnot. And so what we do in modern times is we make proofs so-called non-interactive. This is what Fiat Shamir achieves. It's a fancy way of turning this type of discussion into a one-shot proof. So in modern zero-knowledge proof systems, Alice just sends one message to Rabbit. Rabbit does some verification on it and is then convinced that Alice, in this case here, knows the secret key. So about the properties we want from such a CK-proof system, there are 3 of them. One is completeness. So if Alice has the knowledge she claims she has, whether it's a Sudoku solution or the fact that she's older than 18, she should be able to convince Rabbit about that. That's completeness. So an honest Alice is able to convince Rabbit. On the other hand, it's important for Rabbit, to make this useful for Rabbit, it must be sound. Sound means that if Alice has not the knowledge, she should fail in convincing Rabbit. So if she only has a partial solution to the Sudoku, the proof should fail. And Rabbit should see that kind of Alice is lying here. And then finally, this is kind of so far it's just a proof of knowledge, and then here comes now the zero knowledge component into it. At first this sounds a bit like confusing, right? I'm proving to you that I have knowledge, but why? What's zero knowledge? The idea of this is pretty simple. You should only learn the fact that of the thing I actually want you to know. So in case of the Sudoku example, that means you should only learn I know the Sudoku solution, nothing else. You should not learn any hint that makes it easier for you to solve the Sudoku afterwards. Or in case of this secret key, you should just learn the fact I know the secret key. You should not learn, say, the second bit of it. So that's this so-called zero knowledge property here. This, of course, can be formalized and is done in the literature, but we don't have the time to do so here. So if you care about this type of proof, I recommend you going into the literature and read up on it. So now we can go back. So this is kind of the tool we want to use. And we want to make a verifiable presentation using ZKPs. So the zero knowledge proof here kind of replaces the signature from before. So here on the left, this is our typical verifiable credential you get. It has some metadata in it. Then comes like all the attributes. So that's what you get from the issuer. In case of an ID, this is like first name, family name, your birth date, country of birth, residence, and so on. You know, whatever is on your driving license or passport. That's all in these attributes. You have a holder identifier. That's just in most cases a public key again. And then at the bottom, you have a signature from the issuer on this. And as I said, in theory, you could present this to a verifier, and they could verify it without issues. But because we want to hide the attributes which we don't need to reveal, what we do is we make a verifiable presentation. It has kind of the same structure. There's some metadata about it. Then comes the derived attributes. This could be as simple as I am older than 18. And there comes a fresh holder ID. And the idea of this is we want to hide the fact that we might be here for a second time. So if I go to your shop and I buy a beer twice, ideally you shouldn't learn from the verifiable presentation that it was me again, right? So that's why there is a fresh holder ID. And then instead of the issuer signature, we use a CK proof as kind of this thing. And again, the CK proof has these properties of soundness. So if my original credential actually has the right attributes, you know, I'm really older than 18, then this CK proof should convince you. On the other hand, if I'm too young, I should not be able to generate a verifiable presentation that claims I'm older than 18. That's the soundness property. And then finally, the zero knowledge property makes sure that if you see this verifiable presentation saying I'm older than 18, you will learn nothing about me else. So in particular, you don't learn my birth date, you don't learn my first name, and so on. So that gives us a very fine-grained control over what we reveal in case of verification. And this is, of course, great for you as a user. It empowers you. You can decide when to use a credential, under what conditions. So CK proofs, we have kind of two versions of them. One is directly derived from the credential you get from the identity provider, say. And the technical statement, what you prove here is you say, I know a signature from the issuer on my attributes, and these attributes that were signed satisfy the following derived attributes, like a predicate of it. You can also do it indirectly. In case payment is involved, there is a more efficient variant of it. So whenever you open an account with your identity credential, you will add some so-called commitments to your attributes in these accounts. You can think of these commitments, if you have never heard of that, as some form of like envelope. The value is inside, but no one can look into it. And then again, I can use the magic of zero-knowledge proofs to kind of point at the envelope and say, I know the value inside here, and here's a statement about the value. And so when you open an account on the blockchain, you create these envelopes. And of course, you use CK proof to prove that the envelopes contain the correct values. So now you can directly prove from your account and say, here's my account, and my identity attributes related to this account satisfy the following predicate. Again, simple example is like, say, I'm a resident in the EU. So that's what you can do there. This, of course, is only is primarily useful if you already use the account, say, related to a payment. Other than that, if you do the direct one, you have kind of this ultimate privacy where you do not reveal anything about yourself. Then, in terms of types, this is maybe more for the technically inclined here. There is, of course, in today's world, there's a lot of options you have in terms of CK proofs. You might have heard of GROT16 as a proof system, which allows you to prove arbitrary statements and whatnot. The problem here is that if you use a full-fledged proof system, that if you want to make or create proofs on a mobile device, things can get complicated. Now, in our design here, we aimed at simplicity. And so the statement, as Dragos mentioned, you can prove are of the form like, you can reveal a value. You can show that the value is not equal to a fixed value. And you have these range proofs and set membership proofs. And we believe, for the moment at least, that we do not need any more complicated statements to prove. Now, of course, right, you could imagine a world where someone wants to make a proof of the form like the second bit of my last name matches the first bit of my birth date encoded in a specific form. However, it's very unlikely that you see such a statement in practice. It seems that these very simple type of statements are enough for most reveal proofs you do. And so that allowed us to say, okay, we can go with very basic, well-known protocols, which is easy to implement, means also you have less surface for bugs, and they're true and tested. I mean, Sigma protocols we know for over 20 years, so that gives you a very safe system, a sound system you can trust. And so Sigma protocols are used for the revealing attributes, like, say, a family name. On the other hand, we have bulletproofs. Bulletproofs are for the more complicated statements. I mean, the original bulletproof is built for range proofs. That can be used, for instance, to show you're older than 18. However, we slightly extended the concept because it turns out that this is like has a nice property in there, like an inner product proof. And you can also use this for creating set membership proofs. So you can prove like I'm from country A or country B without specifying from which of the two. And of course, we also have set non-membership. This is kind of just showing you are not in a set. Yeah, so with that, I am at the end of my part. If you want to know more about this, oh yeah, an example about set non-membership. Oh, this could, for instance, be, let's say, you want to buy some special component, electronic component, and you are, you know, in today's world, right, it could be that there is a certain sanction list. So you are not allowed to buy this component unless you can prove you're not from a certain list of countries. So there you would use a set non-membership. You would say, I'm not from these countries on your blacklist, typically. But of course, you can use the concept of a set non-membership also in any other way. Like it works for any attribute you have. You can also prove like my family name is not one of those, just in case. Yeah, so if you want to know more about this, here are some resources. We have developer docs. We have an overview of on the ID. There's also more information about the identity processes, and that's a particularly nice one. We have a proof explorer, so you can kind of go and test this ZK proofs I just mentioned about, and you can, I guess, go to testnet, create an ID, and then play around with it. So that I mean, even for me, who still I mean has done tons of testing with it, it's still fun to do. So yeah, any questions?
There is a question in the chat regarding how the thresholder ID is created, if it's from derived keys, and I'm sending an article right now from our docs which goes deep into that.
Yes. Yeah, it's basically a random identifier on the fly, because you only use that kind of during the exchange and never after. So it's ephemeral. Any other questions?
Any more questions, guys? Sweet. If you guys do have any more questions, you can stick them in the Discord, and I'm sure Dragos and Daniel can answer these later if you can't think of any at the moment. Oh, there's another one coming. Do you guys want to quickly answer that one?
Yeah. So the identity solution line with standard, it follows what the W3C has in terms of like identity. I mean, you've seen kind of my slides on the self-sovereign identity. It's of course kind of aligned to that. The EU DI standard for wallets is still a bit in progress, so this will be a thing for the future, I guess, kind of to ensure compatibility once we know how the wallets actually look in the different countries.
There's a question before even setting up a test account on the wallet, the web wallet was prompted to upload an ID to a third party. Is there any test account? So when you open up the web wallet, you will see in the top right some text that says mainnet. You probably selected mainnet, and that's why it actually asked for an ID. But if you select testnet, you can click on the test identity provider, and you won't have to actually provide your actual ID in order to use the wallet with testnet.
Then there is a question about the difference between the DID and Concordium ID. So the DID is a decentralized identifiers. We actually use them. We have our own kind of DID prefix, if you like. It's DID CCD, which allows you to point at accounts, at smart contracts, but also at things like public keys. And so we use those in our ID system. The Concordium ID is a verifiable credential system built along the lines of W3C. So it's kind of built on top of DIDs. DIDs are used to identify, for instance, verifier, holders, or the issuers.
Okay, awesome. I think that's going to be wrapping it up then. Yeah, like I said, if you guys do think of any other questions, then just drop on the Discord. And if you haven't joined the Discord already, you can join the Discord channel through the platform. There's a link on it on the main homepage, and we have a bunch of different channels there. We can ask technical questions and introduce yourself. And then there's an announcement page where I'll be letting you guys know when the next webinar is coming up. The next one is same time again next week, Tuesday at 4 p.m. UK time, which translates to lots of different times across the world, but same time again. And next week, what do we have? We have Doris joining us for another webinar. This one's going to be an hour long as well, and this is going to be on verifying access. So we'll be looking at exploring Concordium's identity layer in how this can be used in real world verify and access scenarios. And I think this will be featuring practical partner use cases as well. So come again this same time next week to learn more about Concordium. And yeah, see you guys there. All right. Thank you, Daniel and Dragos as well.
Thanks everyone for attending.
Thanks.
Awesome.
Bye.
Bye.
Perfect. Thank you, guys.